Hello second years. So today we're going to be looking at triangles. So we have a diagram here, which as you can see is a three-sided polygon. It is a triangle. And we have three vertices. So they are the corners where two sides meet. And they are each points. So as we know, all points have a capital letter. So we've got A, B and C. We can't have the same letter, otherwise we would get mixed up between points. And it's definitely a different location if you were to imagine it drawn on a plane. Okay, so we can call this triangle ABC, or we can use the symbol. So in mathematics notation, there is a tiny little triangle that looks just like that, and then we label the 3 points of its vertices after it, A, B, C. And we usually like to do things systematically, and that means we'll put them in alphabetical order, A, B, C. Now, of course, it is still correct to be CBA or CAB, but we do like to have it in alphabetical order, just like we do numerical order with things. Okay, now there's some things about triangles that we already know. For example, we can mark their sides and angles to help us know a little bit more about what type of triangle it is. Okay, so we're going to look at some diagrams below to look at some examples of how some markings that I was talking about can be used to indicate certain properties on triangles. So we've got 4 diagrams here. So if we look at this first one, then you will notice that we have the same little marker somewhere in the middle of each of these sides. Just one marker, a little line going through it. And what that tells us is that all 3 of those sides must be equal in measurement. So all 3 sides are the same length. Okay, I'm just going to skip and go to the second one. Now you'll notice on this triangle, this time we have those markers again, but only on 2 sides. This third side does not have the marker. So what this is telling us is that the 2 that do have the marker, they are equal in length, but not with this one. So we've got 2 sides the same and a third length that's different here. Can you remember what this type of triangle is called? If you said isosceles, then you would be correct. An isosceles triangle has 2 equal sides. So can you remember what it's called when a triangle has all 3 sides the same length? It's equilateral. Now, this time we're not looking at sides, we're interested with angles. And you'll notice that inside these angles, we have dots. The same amount of dots in each of the 3 angles. Then this also means that these angles are the same in size, the same amount of degrees. And again, if all 3 angles are the same, then all 3 sides will be the same length. This is again an equilateral triangle. Can you guess how much each of these 3 angles will measure in degrees? If you said 60 degrees, you'll be correct. It doesn't matter how big the triangle is, if all 3 angles are the same and all 3 sides are the same length, then it's an equilateral triangle. And every equilateral triangle that exists has all 3 angles in its vertices of 60 degrees. So let's have a look inside this triangle. Well, we have just 2 of the 3 angles with these same markers, dots, to suggest that they are equal in measurement. So this triangle has 2 angles that are the same and not the third. This one at the top here will be different from these 2 at the bottom. And again, this belongs to this triangle. these are both an example of an isosceles. Every isosceles has two equal sides, and at the bottom of those two equal sides, so the two angles where those two sides do not touch, see how they both touch each other up here? Well, the angle that's created where they touch each other, that will not be the same as the other two angles. That's the odd one out. But the two that are at the bottom, almost like legs, if you imagine this to be a leg and there its feet, they will be the same as each other. Okay, so we've established that there are three types of triangles based on their sides lengths and their angle sizes. And here they are then, just to recap. So we just talked about the equilateral. We first of all looked at how the three sides are the same, and we use a marker to show that, and that all three angles will be the same, but not just the same, they will all be 60 degrees. And that's because for every single triangle that exists, no matter whether it's equilateral, isosceles, or our third category, which we call scalene, all three angles inside will add up to 180. And if these three have to be exactly the same in measurement, then that's the same as splitting our 180 degrees into three equal parts, so dividing it by 3. And 180 divided by 3 is 60. So look, here's our isosceles. Two sides are equal, and at the bottom of those equal sides, so not the angle where the two of them touch, they are equal as well. So two sides are the same length and two angles are the same length. And then last of all, what happens if we have no markers, no dots in our angles? Well, that suggests that this triangle has no sides of the same length and no angles the same length. And that makes it a scalene triangle. I always think of it looking like a little bit like a witch's hat. It's all skew width and out of shape. And witches I associate with a word like scaly. And that helps me remember that. Another type of triangle is a right-angled triangle. And we know from when we did our previous geometry lessons that a right angle is 90 degrees, like the corner of a page. So that helps us to understand that this type of triangle will indeed have a 90-degree angle in it, like the corner of a page. So here we have it. And if you recall, we learnt two different ways to represent a 90-degree angle. We could put a little corner mark like this, or we could put a little box in. So the box would come across and go down like that, something like this. Now, a triangle is a right-angled triangle if one of its angles is a right angle, the 90 degrees. But that means that the other two angles could be varying amounts, but together they will both add to 90 as well, if all three angles, as we just discussed, must add to 180. Now you'll notice that we have quite a large word here. It's called a hypotenuse. Now hypotenuse is the name for the side on a right-angled triangle that never touches the right angle itself. Now it's almost like it's opposite it. So if I was to approach the right angle and put an imaginary line and keep going, I would cross one side of the triangle only, and that's the side that we call the hypotenuse. So some people like to remember that the hypotenuse is opposite the right angle, or alternatively, it's the side that does not touch it. So look, here it is. That's not the right angle. It's not touching it there, and it's not touching it there. So a right angle triangle can either be isosceles or it could be scalene. So we could have both of these two angles, the opposite angles from the 90 degrees, as 45, and that would make it an isosceles triangle. So if you imagine we made this a little bit wider so it was 90 degrees, then the two ends would be 45 and 45, and that would be an example of an isosceles that's also a right angled triangle. Alternatively then, which looks like this one, it will be scalene. So these two will be different to each other, and neither of them will be 90 degrees, so they will all three angles be different. So we're going to be looking at a new theorem that's associated with triangles, and it's Theorem 2. Theorem 2 says that in an isosceles triangle, the angle opposite the equal sides are equal in measurement, which is actually what we've just discussed, the properties of an isosceles triangle. But did you know that that was an actual theorem? So here we have triangle ABC. We have one angle at the bottom of one equal side, and we have the second angle at the bottom of the other equal side. We can call them angle A, angle B. And the theorem tells us that if this side length, now remember these two lines means the distance between. So the distance between A and C means the measurement of this side AC. If that is equal to the measurement of the side AB, then the two angles at the bottom, this one and this one, they must also be equal to. Now the converse of that, which we know means the opposite, we can take it the other way round. If we have a triangle and we find all three angles, or we even just find two and note it is not 60 and 60, but the two angles are the same, then we know it can't be equilateral, and we can deduce by Theorem 2 that the triangle must be isosceles. Now, there we have it. There is the notation for the converse. If angle A, this angle inside a triangle, is the same as this one, then that tells us, this implies that these two side lengths must be equal in measurement also. So in this lesson, we're going to look at two more theorems that are associated with triangles, and they're Theorem 4 and Theorem 6. So far this week then, after this lesson, we will have covered all theorems from 1 through to 6. Okay, so first let's look at Theorem 4. Well, that's the statement that we've been mentioning throughout this class already, that the angles in a triangle add to 180 degrees. So here we have an example triangle, and we've got three angles inside their vertices, and we could label them like this, 1, 2, and 3, or letters, it's up to you. And remember that we have these lines to say the measurement of. So we have the measurement of all three angles added together. Angle 1 plus angle 2 plus angle 3 will give a total number of degrees of 180 degrees, and that's Theorem 4. Now Theorem 6, this is a little bit different, something that you may not have come across before, so we're going to make sure that we really pay attention here. And this says that each exterior angle, now we actually haven't looked at any exterior angles yet. All of these angles inside a triangle are interior angles. Interior means inside something. So an interior designer designs how we decorate inside our houses, for example. The exterior is outside. So the angles outside of the triangle, what does this look like? Well, an exterior angle of a triangle is the angle between one side of the triangle and the extension of an adjacent side. Let's take a look. So, if I have my regular triangle and I continue one of the sides a little bit further than its end point here. So instead of stopping there, I just continue it on. Well, that has created an angle here. It's not inside the triangle, but it is just connected to one of the interior triangles. This part is what we call the exterior angle. So in this diagram, we could label this the number 1. Now, Theorem 6 then, so let's read it again, says that each exterior angle is equal to the sum, and we know that sum means total, adding, of the two interior opposite angles. Now that means it is equal to both of the angles inside the triangle that it is not touching. So the opposite angles, that's this one up here and this one up here. In other words, if I added the measurement of this and this together, it would be exactly the same as this one here. So let's have a look at that. Angle 1 in this diagram is equal to 2 and 3 put together. Now we can actually use a little bit of logic and our common sense and some of the mathematics tools that we've already got to help us understand why this happens. If you imagine that this is a straight line producing a straight angle, so if we include this interior angle of this triangle as well as angle 1 here, that's going to make 180 degrees. The same way that all three of these angles inside the triangle make 180 degrees. So they have something in common. This plus this, our interior angle, makes 180, and so does 2 and 3 plus our interior angle makes 180. So therefore it helps us understand that, well, together they must measure the same amount of degrees. Okay, so we're going to look at some examples from your textbook now, and this is worked example 18.5, page 296, but we've got a triangle and two of its interior angles are labelled 50 degrees and 70 degrees, and we have been asked to find, without measuring, so no use of protractors, the distance between. So if we look at the symbol notation, we've got the two lines, that means the distance between, or in case of an angle, as this little symbol suggests, the measure of. So the measure of angle A. So we're finding the missing angle. Now this is actually testing our knowledge of Theorem 4, that we know that all three angles sum, so total, 180 degrees. So how would we write that with full workings using correct notation? So here's our solution. We would write out Theorem 4. We know that the missing angle plus the two that are given will equal 180 degrees because there are 180 degrees in a triangle. So we've given our explanation, which is Theorem 4. This implies, that's what this symbol is, the arrow, that angle A equals, well, if we move the two 50 and 70 to the other side of the equation, so we take them away from its total, therefore, 3 dots, therefore, angle A is 60 degrees, and don't forget your degree symbol. Page 297, we've got worked example 18.6. Find the measure of angle ABC. Now remember from my last video, I explained that means we need to follow the path from A to B to C to figure out which angle it is it's asking for. Well, it's asking us for the one at the top there. A to B to C is asking for this one here, so we can just label it to help us. Now there was some information on this diagram that's really useful. The fact that it has these two markers, and those markers tell us that those two sides, because there's no marker on this one, those two sides are equal in measurement, and that means it's an isosceles triangle. So if it's an isosceles triangle, then that also means that the two angles at the bottom of those two equal sides are equal in measurement too. So that's why we've got a label for all three of our angles here. We know that C is now 40 degrees. And once we have two angles, we can work out our third by taking the sum, the total of those two angles that we have. So 40 and another 40, because these two must be the same. 40 plus 40 is 80. If we take that away from the complete total for the three angles, 180, then that tells us that angle B, or angle ABC as it was given in the question, is 180 degrees. So let's have a look at our calculations, our workings. We know that we must always give full workings in all answers. So angle C, because angle A is 40, is also 40, and we've explained why. So there's our reasoning, there's our workings. It's an isosceles triangle. And we know that all three angles must equal 180 degrees. That's theorem 4. And this implies then that if we remove those two lots of 40 from the 180, so it's like we've moved both of those from this side of the equation to the other. And we know that when we move something from one side of the equation to the other, we take it away. It doesn't matter whether it's algebra or not, but that's the same process. And 180 take away 40 and another 40 makes 100. And be careful to remember your degree symbol at the bottom. Okay, last example. So worked example 18.7, still on page 297. So find angle C without measuring. Now, we can clearly see that this is an exterior angle. The fact that this side has continued on past its vertex there. And we know from Theorem 6 that exterior angles are equal to the opposite interior angles, the sum of them. And that makes 80 plus 50. Well, that's 130 degrees. So therefore, angle C is 130 degrees, and that's because it is an exterior angle. And it would be okay to use exterior, or you could even write Theorem 6. 1.8, page 297, we have got a triangle and then an exterior angle. So it's just the extension of one of the sides of the triangle, creating this exterior angle. Now we know from Theorem 6 that that measurement is the same as the two opposite interior angles added together. So the same as 1 plus 50 degrees. And our question is asking us to find out this missing interior angle, angle 1. How much does that measure? Now the fact that it says diagram not to scale tells us that we should not be using a protractor, that we're using our knowledge of geometry and theorems. Okay, so if this and this, angle 1 and 50, make 110, then we can simply deduct 50 away from that total, and that will give us the part that 1 was. So let's see how it's written down with full workings. We write down the knowledge, our exterior angle theorem, the two angles inside, number 1 and 50, makes a total of the same as this exterior angle. And we could write exterior angle. This implies then, so if we move the 50 to the other side where it becomes minus 50, so we're taking it away from the total, that the angle is 60 degrees. Therefore, angle 1, 60 degrees. Questions 5, 7, and 9. See you in class tomorrow.